9.3, rotations. Now to do rotations, you will absolutely positively need a protractor to measure the angles, and you can either use a compass or a ruler to measure the lengths. So you must have a protractor for this. All right, rotations are when we rotate our figure. Now in rotations, the size, the shape, and the orientation stay the same. Okay, so they're going to be congruent and our orientation is the same. So let's look at our first concept here. A rotation of x degrees, this is going to tell you how far your figure rotates. A rotation of x degrees about a point R, and this point R is called the center of rotation. So you can think of that like as the middle point on a clock, and the hands rotate around that middle point. So if we look here, our center of rotation is here at point R. We should put that in red. Okay. Here is our center of rotation. And there's a couple important things about this. The image of R itself, or is itself. So if a point on your figure is on the center of rotation, your image is just the same spot. It just turns around in a little circle right here and doesn't go anywhere. This is very similar to your point being on the line of reflection. So that one's easy. For any other point, okay, so point V that is not on the center of rotation, the length RV prime, this is length, equals the length RV. So let's look at that. R to V and R to V prime, these lengths are congruent. Okay, that makes sense. These are just the hands of the clock and we're just spinning it around in a circle. The positive number of degrees that your figure rotates is the angle of rotation. Okay, and we always, in this book, unless otherwise stated, rotations are counterclockwise. Positive number of degrees is counterclockwise. That means we go this way around our center of rotation. And because our size and shape stay the same, a rotation is also an isometry. Everything we've done so far is an isometry. Translations, we just slide them, doesn't change anything. Reflections, even though we flip them over, they are still congruent figures, so an isometry. Rotation, we just spin it around, so it's an isometry. Now your pre-image and your image are equidistant from the center of rotation. Okay, so we're just going around the circle like that. And we're doing that for all of our points. Let's do the first problem on how to draw a rotation. These are the steps you are going to need to follow. So we want to know the image of triangle LOB for a 100-degree rotation about C. So C is our center of rotation, and we're going 100 degrees counterclockwise. Don't forget, rotations are always counterclockwise. So step one here. We find our point C, our center of rotation. We always need to know where that is. And the first thing we're going to do is draw a line from our center to a point, and we are just starting on center O, or point O here. I do this one in red, so we'll do this one in red. So we draw a line to point O, and then we take our protractor and we measure 100 degrees. Okay, so we take our protractor, let's do this whole thing in red. We draw CO, and we use our protractor to measure 100 degrees counterclockwise. And then, so we'll measure, and you put a little dot out here, and then you draw this line. Okay? And then step 2, we use a compass or a ruler, and we take our compass and we draw a circle until we intersect this line. And once we intersect our new line here, we know that this is going to be point O prime. Now, we know that these are equidistant, so we could also just take a ruler and measure the length of CO, and then go to the line we drew with our protractor and measure CO prime. And you put it out here. So compass or ruler will do that. So we have O prime. And then we do the same thing. We take point B, we draw CB, we take our protractor, find 100 degrees, and we draw a new line. And then we take either our compass or our ruler, and we measure the length of CB, and we make CB prime, or we take our compass until it comes here, and then we have point B. So we now have point O prime and point B prime. And then you guessed it, we take our third point, point L, we draw a line to point L, we take our compass, measure 100 degrees counterclockwise, draw a line, and then our ruler, we measure the length of CL, and then we come over here and we make CL prime the same distance, or we take our compass and come around here till we find that intersection. Okay, so we now have O prime, L prime, and B prime. And then we simply connect L prime, O prime, B prime, and we have our new triangle. And it is rotated 100 degrees counterclockwise about our center of rotation. So go ahead, pause the video, and do the next problem. All right, so this says to do a 50-degree rotation. Don't forget you're going counterclockwise. You might want to remind yourself, go in that direction, about B. So point C here means nothing. We are going about B. So I take my red pen and I mark my center of rotation. Now B is on the center of rotation, so I know it just turns into B prime. It can spin around as far as we want it to, and it still just stays right there. And then I chose point O, and I drew a line from my center of rotation to point O. I took my protractor, measured 50 degrees counterclockwise, and then I took my ruler, or my compass, took my ruler, and I measured the length of BO, and then I measured along my new line, and at the same point I put O prime because it is equidistant from the center of rotation. And then I just repeated that for point L, 50-degree rotation, measured BL prime, and put my dot and just drew my new triangle triangle, L prime, O prime, B prime. All right, not too bad. Okay, how do we use these? Well, the center of a regular polygon is a point that is equidistant from the vertices. We are very familiar. Remember, regular polygon means everybody's congruent. Sides are congruent, angles are congruent, everything is congruent. All right, so we have seen these before. Remember when we circumscribed a circle around them and then found the areas? Well, we know that the center is equidistant from the vertices because these vertices are just the radius of that circumscribed circle. And so when we draw in these radii to the vertices, we get congruent triangles, and we know that. Okay, we've done this before. We can use this to find rotations of regular polygons. So let's look at our first example here. It says point X is the center, I like the center of my rotation, a regular pentagon PENTA. Oh, isn't that clever? What is the image of the given point? Oh, that's going to bother me. What is the image of the given point or segment for the given rotation? So we want a 72-degree rotation. Remember, we're going counterclockwise. Let's draw a little arrow there. Remind myself of T. That means we're rotating T about X. Well, we have 5 congruent triangles here. We know how to find a central angle. What is the central angle of each one of these? We simply take 360 divided by 5, and we get 72 degrees. So each one of these is 72 degrees. And so I am taking point T, and I am going to rotate it 72 degrees about X. Well, a 72-degree rotation takes me here to N. So T maps to point N. When T rotates 72 degrees about X, it moves one vertex counterclockwise because we know that's our central angle. The image of T is N, so T maps to N. That would be T prime if we wanted to use prime notation. All right, the next one says a 216-degree rotation of segment Tn about X. So I'm going to move segment Tn and I'm going to rotate it around. And how do I get 216 degrees? Well, is 216 a multiple of 72? Let's find out. As it turns out, 216 degrees divided by 72 degrees is 3. We are going to move 3 spaces. So we take our thing and we go 1, 2, 3. Right? This is like moving T 216 degrees and N 216 degrees, but I like to think of it as moving the entire thing 1, 2, 3. So segment Tn maps to segment. Where would T be and where would N be? Well, if you need to, you know how to turn your paper. T is on the left. P is on the left if that were on the bottom. P, A. Order matters here. Okay? If we go around, this would be T and this would be N. So for a 216-degree rotation, Each vertex moves 3 vertices, so the image of segment TN is segment PA. Now go ahead and pause the video and do the problem. All right, we are asked what is the image of point E for a 144-degree rotation about X? Okay, we take 144 divided by 72. That means E is going to move 2 vertices counterclockwise. Don't forget that we're going counterclockwise. And so it moves around our pentagon up here. And point E maps to point A. So the image of E is A. That wasn't too bad. Let's look at our next example. How do we find the angle of rotation? Well, I have a feeling that this is just the opposite of what we just did. All right, hubcaps of a car wheel often have interesting designs that involve rotation. What is the angle of rotation in degrees about C? So we need to find point C. Point C is right here in the middle. That's our center of rotation. That maps point Q to point X. So we are starting here at point Q, and we are going counterclockwise all the way around to point X. Well, how are we going to figure this out? Well, we need to know how many vertices does Q move? How many vertices does our whole thing have? Well, let's count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9. So N equals 9. We have 9 vertices, 9 sides. How far does Q move? Q moves 1, 2, 3, 4, 5, 6. So this is 6 vertices to get around. So we need to find what does a central angle measure. We know how to do that. 360 divided by 9 equals 40. So each one of our triangles here, right, measures 40 degrees. And I know that I move 6 vertices. So 6 times 40 is 240 degrees. So our angle of rotation is 240 degrees. Pause the video, do the next problem. All right, 3A says in problem 3, what is the angle of rotation about C that maps M to Q? So I start here at M, I go counterclockwise around to Q. It happens to be 6 vertices, same as the last problem, 6 times 40, it's another 240 degree angle of rotation. So that one was really easy. All right, part B says if a 50-degree rotation about a point P maps A to B. So I just drew a little circle here. I've got center P, and I know that from A to B, going from A to B counterclockwise is 50 degrees. Then it says, what angle of rotation maps point B to point A? Now, you may want to say 50 degrees, but don't forget we have to go counterclockwise. So we have to start at B and go counterclockwise around to A. So we have to go all the way around the circle. 360 minus 50 is 310 degrees. Again, pictures are your friend. Draw, 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 and label, label, label. And you know how much I like color. All right, let's look at the next part here. Ooh, this is the last section. A composition of rotations about the same point. So composition, we know what that means. That's multiple rotations. So we would go from A to A prime to A double prime to A triple prime. About the same point is just another rotation about that point. Remember when we did 9-1, we said that composition of transformations is more than likely just another transformation in itself. So what we do is add the angles of rotation to find the total rotation, which makes perfect sense. So if we look at our problem here, it says, what is the image of KITE, quadrilateral, KITE, for a composition of a 30-degree rotation and a 60-degree rotation? Well, we could take our kite here and we could rotate it 30 degrees, and then we could rotate it another 60 degrees. But what would we be doing? We would be rotating a total of 90 degrees. So what we can do is simply rotate the original 90 degrees. All right, pause the video and try the last problem. All right, it says, what are the coordinates of the image of point A at -2, 3 for a composition of two 90-degree rotations about the origin? Now we could do this as two 90-degree rotations. First thing I did was draw myself coordinate plane here, and I could do two 90-degree rotations. And so I would measure 90 degrees and measure how far out it is, and then measure another 90 degrees, measure how far it is. We know how to measure distance on a coordinate plane, okay? Or we know that a composition of rotations, I simply add them together, and 180 degrees is just going to be a straight line through the origin, through our center of rotation. Now, coordinate planes are kind of neat in that if we go over -2, up 3, if I'm going 90 degrees, right, I go 2, 3. And then if I wanted to rotate it one more time, I would go 2, 3. So you can do it that way, right? Because these are just right triangles, and I'm just imagine that triangle and rotating it around. So there's many ways to do this. We could use our protractor and our compass, but on a coordinate plane, we know that 90 degrees is going to be perpendicular. So we would find our slope and find slope perpendicular, which we remember is opposite reciprocal, right? And we could draw in our new slope, or we know 180 degrees is just down the other line, or we can just move it around. Now what I want you to look at is the coordinates of all of these. Our pre-image is -2, 3, over 2, up 3. What is our first image? Well, we went down 2, over 3, and then got opposite coordinates here because we moved 90 degrees. Now look at the second rotation here, our A double prime, our image. We went over 2 and down 3, and look at your coordinates. They are exact opposites because we are in opposite quadrants, right? This first quadrant is positive, positive. Second quadrant is negative, positive. Third quadrant is negative, negative. Fourth quadrant is positive, negative. So do you see the relationship here between your coordinates? All right, rotations are not difficult. You absolutely need a protractor, and a compass is a really easy way to do this if you're good with a compass. If not, a ruler works because rotations are equidistant. Your points are equidistant from the center of rotation. So you just measure with your protractor, draw your line, and then measure your congruent lengths from the center of rotation and label your new points. Work carefully on these and you'll do great.